Let's record. So you're all on slide 6?
Yep.
Number 1, I gave you the beam reactions for the homework, right? For problem number
175, 1,750 pounds. Like on top, pushing down.
that's not the reaction.
Oh, yeah. R1,
That's the
R2, yeah.
concentrated load downward. So yeah, I gave you the 2 reactions. That's step number 1. Step number 2, draw straight lines down at each significant point on the beam. Okay? And that significant points are at each reaction, concentrated loads in the beginning and end of the linear distributed loads. So these are the lines that you're dropping down, the light lines, and then you'll do a horizontal axis for the V. What's V?
Shear.
Shear. 0 is the value of, that's, so the x-axis is your 0 shear. This is positive, this is negative. Same thing with a moment. Okay, 0, positive, negative. So if you go to the homework, first thing you're going to do, drop a line here, drop a line here, here, and here. Very light lines. Those are your vertical axes. They're just at significant points along the beam. A horizontal axis for the shear and a horizontal for the moment. Everybody okay with that step?
Yes.
Okay. Now, what JN always said is that if you're plotting the shear diagram from the beam, cover up the whole beam. Okay, cover up the whole beam, and so if let me try something here. Fill. So this is, oh, isn't that amazing? So there's your piece of paper, right? So Jane, cover up the whole beam and slowly move the paper to the right. What's the first thing? Now you always start at what on the shear? 0. So your shear always starts at 0. So the piece of paper is covering the whole beam. I move it a little bit to the right. What's the first load that I see?
R1.
Reaction.
R1. So I go from 0 up to the value of R1. So on the homework, that's what you're going to do. Right? For us, it's 2200. For beam number 1, it's for the homework, 3360. And don't worry about the scale. Try to get the scale as best you can on the shear diagram. Okay? Does that make sense or not?
Yes.
Yeah.
Okay. So the first thing we see, we talked about the left end reaction. The reaction arrow points up. So from our starting point of 0, we draw that line vertically, a reasonable distance, which we'll assume to represent the reaction. The next step, number 4, as we slide the paper to the right, we notice there are no new loads or reactions until we get to the concentrated load in the middle of the beam. Don't forget, the first problem is what? There's no beam weight. So I'm moving it, I see nothing. I see no beam weight. So what happens to my shear diagram? Stays constant at 2200. Constant at 2200, right? Till just before, and it stays at 2200, just before I hit that concentrated load, that 4,400 pounder. And step 5 says, as we move the paper a fraction of an inch toward the right, we then uncover that concentrated load. Therefore, we must move vertically downward the magnitude of that load, which is 4,400 pounds, but from the previous value of 2,200. So guess what? You had 2,200. Now you got to drop 4,400. So 2,200 minus 4,400 is minus 200. So that's the value of your shear curve at that point. Now, a couple of you sent me some, just a quick email on your homework, which is fine. That helped me out a lot. And what you did is you labeled this fine. And then for some reason, instead of 2,200, you labeled it 4,400. That's the drop. That's the overall drop at the concentrated load. So from here to here is 4,400. So I start at 2,200 minus 4,400 gives me a value of the shear of negative 2,200 pounds. Okay. No, concentrated load and reactions always have two values of shear, right? This had a value of shear at 0 and 2,200. At this concentrated load, it had 2,200 and negative 2,200. So step 6, again, we slide our paper to the right. We notice that there are no new loads or reactions until just before the right end reaction, which is a concentrated load. Remember, we are assuming no beam weight. So we go to here, right? And what is that shear curve looking like? It stays at negative 2,200. Whoops, I hit something. And just before that end reaction, it's still at negative 2,200. And I decided not to post the PowerPoint. I'm just going to give you the PDF, okay? And then once we uncover that right end reaction, we've got to go up or down from this point. Up, because that reaction is facing up. So we follow the yellow brick road, or the orange brick road, up to 0. Any changes that I make, I'll post to Vanco. And that shouldn't have a negative in front of it. There you go. So do the steps make sense?
Yes.
Yeah.
Okay.
Yep.
And I don't know, I think this helped me out a little bit in terms of how to explain it. I'm going to put this off to the side so I can go capture it again. So that takes us to the moment curve. Okay. Now this is where you have to label the areas under the shear curve. This is a rectangle. This is another rectangle. This is area 1, this is area 2. Area 1 is going to be positive, area 2 is going to be negative. Okay. So the moment diagram is a graph of the bending moment along the beam, but it really is a function of the areas under the shear curve. Now, a couple of you sent me your homework, but you didn't show me the calculations of this area. You just gave me the value of it. I'll probably send you an email back saying, give me the calculations of the area. Okay? That's where you lose credit. So I'll email you back if you didn't do that. So, area 1 is a simple shape. Its area is easy to calculate. And the area is positive 2,200 times 10 feet. And so that's positive 22,000 foot-pounds. A shear force times a distance equals a moment. Area 2 is also a simple shape. And because this is a beautiful beam, it makes sense that it is the same as area 1, only it's negative. Okay, so I always go through and I calculate the areas first off to the side. That's what you got to show me on your homework. Okay, especially when you get into, you get into trapezoids. The moment curve always starts at 0 unless it is a fixed end reaction. Our beam is a simply supported beam. So here the moment curve starts at 0. Value of the moment curve at this point is the value of area 1. And that's the maximum moment. Did I talk about the V? Oh, the Vmax here, folks. This is critical. This is back on slide 6. The maximum shear is the greatest absolute value of the shear curve at any 2 points, or at any 1 point. Not the shear between here and here. The shear at this point is what? 2200.
100.
The shear here is an absolute value of 4400. And here the shear is 2200. Some books differ from Mr. Altanius and I. We were always taught to use the biggest absolute value, which really means the maximum shear is always the biggest of the loads.
I have a question.
Yep.
So if it has the biggest shear value, does that mean that's where something will shear if it does end up breaking?
Yep.
Cool. Thank you.
Yep. And when we get into analysis of beams, we're going to give you a shear stress formula. And then we're going to get into a bending stress formula. So the shear stress formula deals with the biggest shear load. And the biggest bending stress deals with the largest moment on the moment curve. And then we also have to know where they occur. So maximum shear occurs at the middle of the beam. Maximum moment occurs at the middle of the beam. That's not always going to be the case with beams that are not beautiful or symmetric.
So that moment curve wouldn't actually be a curved line. It would be
No, that's a good question. That's a good question. Because there's no beam weight, the shear curve is a flat straight line, right? And I think I put, look at step 5. If the line between 2 significant points on the shear curve, right? The V curve is the shear curve. If that line is horizontal, then the equivalent interval on the moment curve is a straight sloped line, sloped up or down depending on the value of the points to be connected. It's really like a parabola, okay? And again, note, see how the M value at the end of the beam equals 0. And that's going to be our check. Check on the shear was when we analyzed the loads, almost like a road map, we started at 0, we followed the yellow brick road, and we wound up back at 0. The moment curve has to end at 0. And on the next example that I gave, there was a slight rounding off error. Isn't that amazing? Sorry. So the value of the moment curve here is the same as the area of shape 1 under the shear curve. The value of the moment curve at this point equals the value of area 1 plus area 2. But remember, area 2 is negative.
Oh, okay.
Okay?
Yeah.
Or you could say that the value of the moment curve here is whatever this value is plus area 2. But again, area 2 is negative. I did one of these for coordinate geometry and surveying. And again, in the discussion that I had with those students, they found some typos and they found some areas that needed clarification. So I'm going to after every Zoom thing that I talk about these PowerPoints, I'm going to repost them. I won't re-email them, but I'll repost them with the date that I revised them. So you can always get the latest and greatest. So hopefully you all, you ever heard of the Beatles? Hopefully you all listen to that movie, Help. Actually, it's a movie and a song. I believe the movie came out in 1965, and I went to see it in the movie theater. I do remember that. A little bit of history there. Okay, so I want to get that right there. And because that was the easy beam, let's go to the homework. And I'm not going to do it for you here, but let's talk about it. So you drew those light lines. Okay. You drew those light lines. You're going to cover it with a sheet of paper. You always start the shear at what?
0.
0.
0. Now, just for the hell of it, get your calculators out. And this is the example that I gave on the difficult beam, beam number 3, which is not due. I'll have that due Monday. So if we don't get to that today, I'll do a little bit of review for that on Friday at 11. And I'll try to record that one as well. So in your calculator, take 0, punch in 0, and then you're going to add what? As you uncover the first reaction.
3,360.
3360, hit the equals button, that's the value of the shear curve. Just like it was in the other example. Right? So you'd go to 0, come up to 3360. As you move that to the right, what do you see? Nothing.
Flat.
No, there's no beam weight. So what's the shear curve going to do?
Stay flat.
Go
Horizontal.
straight.
It's going to stay flat. It's going to stay flat until you get to what?
1750.
1750. So in your calculator, you now have 3360, right?
Mhm.
Now subtract 1750. Hit the equals button. What do you got?
1610.
That's the value of your shear curve directly below. In other words, that drop of 1750 now gives you a shear value of positive 1610. Because we threw 2 concentrated loads at you. Okay? So leave that in your calculator. Leave 1610 in your calculator. What do I do now? Keep uncovering the beam. No. See if that comes up on the recording. Nothing happens until what?
3200.
Now, on your calculator, say minus 4200. What's that value of the shear curve?
Negative 2590.
Right. So at this point on the shear curve, the curve, and really it's not a curve, it's a straight line. It'll be at 1610, and then it'll go down to negative 2590. So those are the 2 values of the shear curve at that point, at that concentrated load. Now what do I do? Just like old JN said. As I keep uncovering that, what's the value of the shear curve? It stays at negative 2590. And now, amazingly, I have to do what?
2590.
2590 up, and that brings me back to 0. That brings me back to 0. So without drawing in my axes, let's see if I can do let's do a shape here. So what did I do? I started at 0. Oops. Almost swore. So then I'll do a,
Sugar Shack.
right, came over to here, do another one, came down to here, about 1610. Came over to here, dropped down, brought me into the negative, right?
Mhm.
Because here was my, whoop, didn't do that right. There's my horizontal axis. And then brought it back up to 0.
Can you divide those shapes up to do your area?
Yes. Well, you have to.
Yeah.
You got to get them into simple shapes. So this is area 1, right? The distance is what? 6 foot? What shear value?
3360.
3360, right. Not 1610. 1610 is the shear value for area 2, right?
Mhm.
That's 1610 times what?
10.
10 feet. And then this area 3 is, what's the shear value?
Negative 2950.
Negative 2950 times 14. And that should bring you back to 0 with the moment curve. Because these are flat horizontal lines, that's an oxymoron. These are horizontal lines. The moment curve is going to look like a what? Sloped straight line.
And so would the moment curve have a different slope at each concentrated load? Like for the 6 feet and the 10 feet and the 14 feet, would those all be different slopes or no?
Yep. No, yes, they will be. Yep.
Mr. McKeegan,
What?
I gotta go to work, but I'm wondering for beam 2 and beam 3. So those have the beam weight in it, right?
Yes. Beam 3
Okay.
is not due till probably next Monday.
Okay, but beam 1 and beam 2 are what's due tomorrow, correct?
Tomorrow at 10, yep.
Yeah. Okay, cool. Thank you.
So
Thank you very
real quick, did he leave already?
No, I'm still here.
So here's the one with the linear load. Now, because it's a beam weight, right? So if I go back to so now if I cover up that beam, same thing. The shear value starts at what?
0.
Goes up the value of the reaction.
Okay.
And then with each foot, how much does it decrease?
100.
100 pounds. So what you can say is you can say that the value here is nothing more than 1,000 minus parentheses 20 times 100, which would give you a minus 1,000, and then whoop, right back up to 0 because R2 is a positive 1,000. Or you could, as JN says, you can plot it every foot, but that takes forever. So every foot, it's dropping 100. Or yeah. And over 10 feet, it's going to drop what? 1,000 pounds, which makes the shear diagram
0. Makes it
0.
cool.
keeps dropping 100 pounds. Every foot, 100 pounds. Eventually, it's going to drop another 1,000 pounds over that second half of the beam. That's going to give you a minus 1,000 shear value, which makes sense because now you go back up to the 0 because the reaction is 1,000 pounds. Then if you go over to here, the value at the moment curve. Hey, before you leave, if I started at 6, is that better for everybody?
Yeah, I work at 7 all day this week.
How about the rest of you? Does it really matter?
6 is
I
better.
like 6 better.
You like
Yeah.
6 better? 6 is better?
Yeah, 6 is better for me.
Yeah, 6 is better.
Okay, anybody not like 6? Like I said, you can just pop in and out as you like. I'm not going to bother with attendance. So here, actually, I don't need that. So let me, that just so I can use it some other day. Okay, now the areas are what?
Triangles.
Triangles. And like I said, a couple of you just gave me the value of area 1 for the homework. You got to show me 1/2 base, which is a distance, times height, which is a shear load. There's your moment, foot-pounds. Now, if the line between the two significant points on the V curve is a slope straight line, then the equivalent interval on the moment curve is an upward curve like a parabola. Okay. See how the M value at the end of the beam equals 0. Again, that's our check. That's our check because area 1 was positive 5,000 foot-pounds. So that's the value of the moment curve there. And then area 2 is added to that, but area 2 is negative, so that brings you back to 0. Or you can say that the moment at this point is the value of area 1 plus area 2. So there's a couple of ways to describe that. Okay. Any questions on this? So that will help you on this one. Now, I did look at some of your examples. You actually did some of the moments. You didn't have to because it's a beautiful beam. And it's a W 18 by 106. So each reaction is 106 pounds per foot times what? Each reaction is responsible for how much of that beam? 1/2. So 106 pounds per foot times 10 feet equals 1,060. Now, Mr. Van Duzen was telling me that Mr. Hultanius actually draws, do you know where that happens to be?
What'd I say?
Well, oh, you're there?
I'm hiding.
Didn't you say that Dave draws with like a stylus?
Oh, yeah. That's usually in Adobe or something. But if you go to your shapes, insert shapes or under your drawing tab that's in the top in the center,
Yep.
insert and then hit shapes. There is a squiggly one under recent used.
Right there.
That's freehand.
Oh, okay.
So
So that reaction is responsible for half the beam. And then you got to go back and get that little squiggly each time. So I'll look to see if there's a,
well, it's now it'll appear in the top left corner. You'll see the little squiggly.
oh yeah, okay, because I've used it. I see.
Yep.
Cool.
Yep.
Thank you, sir.
Yep.
Let's go back to, let's see, we got about 10, 15 minutes, we can look at this nasty one. Anybody taking the time to read this? I don't answer that. Do me a favor, before Friday, try to duplicate those calcs and follow the yellow brick road, actually the orange brick road, as you move along this is the loading diagram, which is called the free body diagram. So as Mr. H has said, and he taught Mr. Van Dusen and I, that you basically are looking at as a road map. You're going up the reaction, you're dropping down so many pounds per foot, you're dropping down a greater slope because now I have the beam weight plus a partial linear load, okay, in that 8-foot section of the span. And then you're dropping back at the slope of 150 pounds per foot along that 12 foot of the span. That'll give you another shear curve. Then you drop down 4,500 pounds. Then you drop down, as you walk along the beam, you drop down 150 pounds per foot. And then you walk back up the magnitude of that reaction.
So each span that is just beam weight should slope, like that line should slope at the same.
And that's a good point. You are basically analyzing the beam at different sections of the span in between significant points. A reaction, a start of a partial linear load, the end of a partial linear load, another concentrated load, and then both the end reaction and the end of the beam itself with its beam. So yeah, you're analyzing sections of the span. And that's where I want you right down here. Remember we just did that for the easier problem where we had you keep your calculations in your calculator. Don't clear it. And see if you can get your calculator to do exactly what I've done here, because that's how you do your shear diagram. I'm not asking you for any calculations on your homework for the shear. I just want the proper labels. And that's why we generated this step-by-step process for your calculator. And then we color-coded each of the shear values for the curve and where they occur in the calculations. If you can do that, I'm telling you, you'll be able to do these things faster and poop through a Christmas goose. You knew I had to say that at some point.
Steve, what about the units quiz? Is that going on?
Yeah, we're gonna probably, after we're done here, Mr. V is gonna show me how to activate that. And thank you for the reminder. And then I think we'll have that due, I don't know, Friday morning. It's an easy one. So keep your eyes peeled for that, okay? And then we'll do another one. We'll do at least one each week. Yep. So let's grab that.
What I'm talking about, I will go after this. I will both be out.
Hey, just make sure you're on.
We don't have a schedule.
I got my reminders, my alarm.
Guys, don't forget I'm recording this, so. Okay, if you go over here, we'll do this. Look, we got a couple more minutes.
Nah, I was figuring out what I was gonna eat, and I was trying to like get some more. I was literally
Okay, so, hey guys, mute yourself, will you please? Okay. So if you cover that whole beam, you move slowly, there's your first end reaction. Now, how much are you going to drop every foot?
180, I think.
150.
150.
So it's 150. If you look down here, it's 0 plus reaction, R1 equals positive 7127.8, minus, in parentheses, 6 times 150 pounds per foot, in parentheses. That should give you a value of 6227.8. And that's the value of your shear curve at that point. Now what we're doing is we're analyzing 8 feet of the span. So leaving that green number in your calculator minus, and actually that should be double parentheses, okay, 8 feet times, but now you got 550 pounds per foot plus 150. 550 plus 150 over a span of 8 feet. That value right there will be subtracted from the previous shear value and gives you a new value of 627.8. Now you're going to analyze 12 feet of the beam, of the span, where every foot you're dropping 150 pounds. So this value right here is subtracted from 627, but now I go from a positive to a negative. So it drops below the 0 line, and it crossed the 0 line. We'll talk about how to find that in the next slide. Okay, now all of a sudden it does what? It just drops 4,500 pounds.
For the negative 1172, isn't it negative 1172.2?
Thank you, sir. That's why I hired you guys. And let's give it the old hashtag. Okay, thank you. Again, step 7, that drops straight down due to the concentrated load. Gives you a negative 5672.2. Now it's going to drop over a part of the span of 10 feet at a rate of 150 pounds per foot. This is negative, adding to a negative gives you a bigger negative. And isn't that amazing? R2 is 7172.2. I'll put this off for use another day. And this is key. I got to be honest with you. Students don't like to do this. I don't know why, but man, that's how you get fast with this stuff. Okay, and I think Mr. V would clarify that a lot of the students are not using our helpful hints to get fast at this stuff in not just structural theory, but in concrete and steel.
What do you say, Steve? Look for the pattern?
Look for the pattern, baby. Look for the pattern. Okay. We had fun firing these up. You know, just a nice pattern. So that give you another instrumental. Oh, we forgot the moment curve. Now here's all of your areas. So off to the side on your piece of paper, you got to show me the area calcs. This will help you for beam number 3, right? Because beam number 3, we have a beam weight. We do not have a partial linear load, but we have another concentrated load. We want you to calculate the reactions. It's not a beautiful beam, so make sure you're still staying up to date on how to calculate reactions. I'll get another cough drop here for a second. So, real quick, this area is a composite shape. I'm on slide 13. And what I mean by composite, it's made up of 2 simple shapes. A rectangle but we can actually calculate it using a formula for the area of a trapezoid, which is really the average of the two shears, right? V1 plus V2 divided by 2 times the distance. Shear 1 plus shear 2 divided by 2 times what? How many feet? 6 feet. 6 feet.
No, I'm saying the word. I know.
What's area 2? A trapezoid or a triangle? It's a trapezoid. Okay. And so we showed you where we got that. So coming down here, again, this should be a smooth curve. I really couldn't figure out, I got a little shaky there, sorry about that. But the value of the moment curve at this point is the value of area 1. This is the value of area 1 plus area 2. Now, remember this thing crossed the 0 line, the shear 0 line. So area 3, we need to find the distance where the shear crosses the 0 line. We can use the slope equation equals rise over run. We know the slope, 150 pounds per foot. We know the rise, it's going to go from 627.8 down to 0. So the rise is 627.8 divided by 150 pounds per foot. That's 4.2 feet. 4.2 feet. 1/2 base times height. 1/2 the base times the shear. That's added to the previous M value, or the value here is area 1 plus area 2 plus area 3. Also, where it covered the shear, where it crossed the 0 shear line, we drew a light line down because it becomes a significant point. Area 4, we can say that 12, the distance between here and here, minus 4.2 gives us 7.8. Or we go back to the equation, okay, minus 1172.2, and that needs a divided by. Okay, 150 pounds per foot equals 7.8. So there's a check for us. In other words, the shear drops from that 0 to 1172 at a rate of 150 pounds per foot. There's the value of area 4. It's a triangle. And then area 5, it's negative, and it's a trapezoid again. Average of the two shears times 10 feet. Okay. So walk yourself through these step-by-steps. And like I said, this one and this one are due tomorrow night at 10. And then this one, I think will be due, I don't know, maybe Sunday night or Monday morning. I'll give you the weekend to work on it.
Beam 1 and 2. Let's do it tomorrow at 10.
Yep, that's what's on Vanco. So you want to stay up to date on Vanco. And let me go over here, and I'm going to hit more, and I'm going to stop recording.